Let's see what we have done. So we know that what does a period what does the so let's go back to this. Okay, so what we have learned, so we know the definition of a orbit. We also define what is a fixed point of a map, and we extend this definition of the fixed point of the map to define what is the uh, periodic orbit of a map. So, and that's and periodic orbit is nothing but the fixed point of higher iterates of that function of that map. So that much we have learned. Now the next question is, so why we are interested in the fixed point or periodic orbit of a map? And the answer is to know whether or not, suppose we start from x0 and its orbit is x0, suppose x1, and it continues, suppose here xn, it continues like that, and suppose its fixed point is some x star. Now we want to know the answer of the question whether the sequence, this sequence, or you can this is the orbit, whether this orbit asymptotically or eventually go towards this fixed point. Suppose it going towards a fixed point which is x star, a point x star, and if once it reaches to the fixed point, it will stay there forever. That's why it's called the fixed point. Whether any initial condition will go towards these fixed points or not, that's why we are interested, because that is the ultimate fate of an system. So if we want to see the behavior of a population, then it is very important to know whether the population will go toward population size of that particular population will go towards infinity, or it will extinct after some time. So it is very important for that particular population. So to know the ultimate fate is our ultimate goal. Now we have seen that to calculate how to calculate a fixed point, and we have seen that how to calculate a fixed point. So we have to solve this equation x equal to f of x, and if we can solve this equation, we can easily, suppose it the solution is x0 and that solution is the fixed point of the map. Now we have seen that sometimes these equation become very tedious to solve. Then we see how to solve by applying a graphical method, or you can see that by using graph, using y equal to x line and f equal to fx line, we have seen that how to calculate its fixed point. Let me remind you. So to calculate the fixed point, we know that if we draw this line, suppose this is fx, so this is fx. If it is fx, then this axis is called codomain axis, and this is the domain, this is fx, and suppose the another axis is y, another curve is y equal to x, suppose y equal to x is this. So where the y equal to x and y equal to fx and y equal to x cross each other, or where they are intersect, this point is called the fixed point of that map, and this is called the fixed point of the map. Now the our goal in today's class is can we use this graphical method to see the fate of the population or the fate of that system, or in terms of mathematics, if I say, so whether if I start from any initial condition, suppose if I start from, suppose a condition which is x0, okay, this is x star, x star. So suppose we are start from this x0. Now under the multiple iteration, whether this iteration asymptotically approach towards this point or not. So or I will say the most useful method to study in case of map, one dimensional map or two dimensional map, that is the cobweb diagram. Cobweb diagram. So let's see how you can go. So first let draw its codomain axis. This is the domain axis. Domain axis x. Codomain axis means where after applying the after iterate what it will go. So that is the codomain basically. This is my fx suppose, and this is my y equal to x. This is the fixed point. This is the fixed point. Now let's see, suppose we start from x0 here. Now if I apply this function, if this is the fx, this is the fx, this is line equal to y equal to x, this is y equal to fx. Now if I want to know if I apply f on this x0, where it will go. So it will become f of x0. So what is the f of x0? F of x0, so if I draw a vertical line, so if I draw a parallel line to the y axis, it will cut somewhere in this here, this curve, that y equal to fx, and where it will cut, where it will cross sex, that cross section will be that the x1, its first iterate. This will be f of x0, and we know that the first iterate of x0 is x1, that is f of x0. So that's how we get the first iterate. So this point will be x will be x0 and y will be x1. So this is x1 equal to f of x0. This part is. Now that is only the first iterate. Now to know its orbit, we have to know the other iterates, that x1, if I applied f on x1, where it will go, I have to know those things also, and I want to use this map to graphically see this. So first of all we have to see, since here is the domain, so if I want to apply f on this x1, I have to take this x1 on this domain axis, x axis. So how can we, because here the x1 is on the y axis, this is the value of y. So one way is to make a reflection in this, make a reflection around this y equal to x axis. So if I reflect, it will become, so this point will become here somewhere, and this blue line will become here, and suppose this line will be like that. So now this point will become x1. Now you see that after reflection and seeing whether it goes or not, it becomes very tedious. So that is not a easy method. So that's why we can use that, but it is not so convenient to use that, because we want a simpler method to check whether what is the fate of the system. And the systematic approach is, first you will draw a vertical line from x0. So let's draw a vertical line from x0, and where it cut the y equal to y x axis, that point will become x0 comma x0. Why it is x0 comma x0? What will be the value of y at this point? So basically y will be y0 equal to x0. So y0 is actually x0, nothing but. So we get the point x0 comma x0. Now if I go further vertically until it reaches the y equal to fx, then at which point it will cut the y equal to fx map, that will be our first iterate of x0. So this point we will get this point first iterate. Now what we will do, from this point we want to generate a point like x0 x0 similar as x1 x1. So what we will do, we will do that, we will now second we are to continue the vertical line, continue the vertical line until it reaches to the curve y equal to fx, and the point it will cut is x0 x1. Now we want to generate from x0 x1 to x1 x1 point. So what we will do, we will now draw up a horizontal line, that is horizontal line from this, and somewhere it will cut the y equal to x axis. So that is, we call it identical axis. This is we will call this identical axis. So it will cut somewhere identical axis. So this point, you see, we know this distance is x1. Since this is the parallel, this line will be parallel to the x line, so this distance will be x1. And we know, since this point is in the curve, so here the value of x and y will be same. So that's how we get a point x1 comma x1. Now Subhusaji, do you get it, or is there any question? So how I get x1 x1?
No, so far it's clear.
Okay.
Quite clear, not totally.
Okay. So then we will get x1 x1. Then again from x1 x1, so we will get x1 x1 from x0. Then again we will go vertically, and since this point is actually x1, so if I go again vertically, it will hit somewhere. So let me, so first this is the second process, let me third process. So x0 x1, third is, now after getting this point x0 x1, from x0 x1 we will draw a line, horizontal line until it reaches to y equal to x card. Now where it and the point will be x1 comma x1. Now our motivation is, we have to generate x2, means the second iterate from the x1. If we applied x1, so we know the x value is here x1. Now we again, since this is x1, this value is x1, now we know, now we get what we want, that the x1 in the domain axis. Now if I apply f on this x1, we will get x2. Now what will the, that means we have to know what is the value of f x1. So this is x1. So if I want to know what is the value of x1, we have to draw a vertical line. So that will hit here somewhere. That will be x2, because that is actually f of x1. So now we get x1 comma x2. And you see, from I don't have to go this far. If I only go to identical axis, and from identical axis if I draw a vertical line, it will give me a point that is x1 x2. And if I continue this process again, after getting this point, if I draw a horizontal line, then it will cut here somewhere. That point will be again x2 x2. And suppose x2 x2, if I want to generate x3, I know I have to know whether the x2 x2 will go to I have to move vertically, and vertically where it hits the y equal to x axis, that will be x3. So let me draw it clearly, then it will be more clear. So let me draw it here again. So this is called the cobweb diagram. So you see that the this is the first iteration x0, this is the second iteration x1, this will be the third iteration x2, first iteration second iteration x2, then I will get somewhere here x3. So let me draw it clearly then. Okay, that is the okay. Let me give you an example, clear example, then it will be more uh, easier to see. So let draw a cobweb diagram for fx equal to x square. Okay, let's see. So this is x axis, this is, suppose let me first draw, suppose this is 1, okay, suppose this is 1, this is 1, this is same as 1. This is our identical line. So this identical line means nothing but y equal to x. Now we have to draw fx. So let us draw this fx. So what we know that what is the value of fx at x equal to 0, that is 0, and what is the value of x square x equal to 1, that will be 1. Suppose f of 0 will be 0, f of 1 will be 1, and okay, ah okay, let me share the screen. Now it is visible, right, Sobhaj?
Yes, yes, it is visible.
Okay. Now, how far you have seen that? You have seen that means I want to let me repeat this part again. So I want to draw a cobweb diagram for fx equal to x square. So for that, what we have to do? So we have to draw y equal to x. Means where when you feel that you are not getting any point, you just stop me. So y equal to, we have to draw the identical line y equal to fx, then I have to draw this curve. And in general the drawing a curve is very useful. So how this Subhuji, can you guess how this curve will look like, fx equal to x square? So uh, so to draw a card, basically there are we you have to check three things. That one thing is that what is its behavior at origin, that means where x equal to 0 is, what is the value of y. So that is, if I put x equal to 0, you will get that is 0. If I put x equal to 1, that is 1. And you have to check what is its slope is higher than this or not. So to check the slope, we know that if I first derivative this function, dy dx here df of x dx will get its slope. So that is basically 2x. So d of x square, this is 2x. Now at x equal to 0, what its slope? Its slope is dy dx at x equal to 0 is 0. So that means, and dy dx at x equal to 1 will be 2. So it is quite larger than 1. So this slope of this axis is dy dx equal to 1. So it came from here horizontally, so like this, and then it will go steeper, and here it's cross like this. So did you get it? Do you get it there, Subhasaj? How I draw the card? Or it doesn't matter.
Yes, yes, it's clear.
Okay. So, okay, that is the first step. So I have drawn this. Now suppose I have to generate the cobweb diagram. So first let me take a point here. Suppose this point is x0. Okay, or maybe let me draw it further away. Here maybe. Suppose I have a point here x0. Okay. So this is x0. Now I have to draw the cobweb diagram. Now what we will do? So let begin the first process. So I have to draw a vertical line from here. So here, suppose it will hit here. So a vertical line. So where it cross the fx equal to x square, fx equal to x square, what will be that point? This point is the first iterate. This point is actually f of x0 is x0 square. So this will be the first iterate. Did you, do you get it? The Subhasachi, this is the first iterate.
Yes, yes,
This
it's clear.
this is the first iterate. So we get the first iterate, and in the identical axis where this point cuts here, I get that the point x1 x0 x0. So this point is x0 x0. This point is x0 x0. Now what we'll do? So now okay, so it goes closer to x equal to 1. Okay, now what we will do, we have to draw a horizontal line. So if I draw a horizontal line, so you see it going closer. Maybe I haven't draw it properly, so okay, let me draw it again, because okay, it is like that. Let's start from here, it will be clearer. So from x0 we got these 2 points. This will be x1. Okay, sorry, let me bring back what we have done again. So this is the x0, this is the x0. If I draw this point, I get x0 x0, and I get this point. This is the first iterate, and it's the y value is x0. This we get x0 x1. Now what we have to do? We have to do that from this point I have to go astray horizontally. So if I astray horizontally here, so I get another point. So that point is basically nothing but x1 x1. Now there, if I again, now this x1 x1, now if I x1 x1 to going vertically towards the curve, y equal to x square, I get a point here, and this point is nothing but the second iterate of this point. So this is nothing but this is x1 comma x2, and if I continue this process, then again I have to take a horizontal line toward this. I will get a point here. This point will be x2 x3, and then it will go here. We get here the point x2 x2, this is x2 x3. Now if I continue this process, so we are started from here, then we go here, then here, then here, it hits here. Now you see, Subhusaji, that this point, this is 0, this is 1. So for x square, fx equal x square, if I take any point which is between 0 to 1, that points actually goes towards a fixed point, that is x equal to 0, because the identical line cross the fx, my function, at origin and at x equal to 1. So you see that the fate of that point is going towards the x equal to 0. So this means that the ultimate fate, suppose here the x represent the population density, and if x square, if x equal to x square is the law which that population size follows, then it means that that population eventually die out, eventually go towards x equal to 0. Now let's check numerically. Let's suppose x is less than 1, suppose x equal to 0.5. So what will be my x1? x1 will be f of x0, that means 0.5 square, that is 0.25. Yes, it is decreasing. Now I have to go x2, that will be f of x1, that is 0.25 its square, it will be, I think, 0.05, right, 25. So you see that we are going that our cobweb diagram showing us correct direction, that every iterate x2 is less than x1 and x1 is less than x0, and this continues towards x0. So that's it, that from the cobweb diagram we can tell, we can see that whether this fx equal to x square going towards x equal to 0, or it does not go towards a fixed point. So here another fixed point is sitting there, so another fixed point is x equal to 1, but you see that any fixed point, any initial point does not go towards x equal to 1, but it diverges from x equal to 1 and go towards x equal to 0. And now Subhusachi, can if you get it, then let do a simple exercise. So now we will want to generate the same cobweb diagram, but where the initial condition will be greater than 1, x0 will be 1. So what will be what is the fate then? Means, have you get this have this cobweb diagram, Subhusaji? Then we will go to the next.
Yes, this diagram is clear. And according to this diagram, any population will go to the near the origin, like it will die out, right?
Yeah, that's it.
Yes, it's clear. It's clear.
So let me again draw another, then it will be more clearer, I think. So now since it is very simple looking map, that's why we can see, I can tell by using some iterates by hand, but when it will become very complicated looking map, you can't tell by this doing this simple iterate, then the cobweb diagram will be very useful. So suppose it's y equal to x, and this is like that. Okay, it's too steeper. Like that. Now let's see where this is suppose 1. This is 1. Now if I want to see the fate of initial condition which is greater than 1, suppose this is x0, where it will go. So let first what we will do, we write it very close. Then suppose we have to take a horizontal line that will hit here. Suppose this point is x0 x0 and x0 x0, and where it is hit, that is x0 comma x1, and then we go horizontally, then it will hit here. This point will become that my x0, oh sorry, x1 x1 x1, and again we will go upward and it will hit somewhere. This point will become x1 x2. Then from here we go here. This point we will see that is actually x3 x3, oh sorry, x2 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 x2. Now from here, now you see, if I start from x greater than 1, that means x greater than 1, then it is going towards infinity, that is diverging. So that's it. That's how we use the cobweb diagram to see the ultimate fate of the any system. Now let's go towards and mathematical things that we are using here, that whether the under the iteration the initial condition will go towards go eventually go towards fixed point or not, or it will diverge. So let us first define what does that mean, that in terms of that whether we are using that words, colloquial words, that the population is dying out or population is going towards infinity. So but in terms of mathematics, those are called the limit of the sequence of what, limit of the sequence of the orbit. So we know, so first let me, so let us mathematize the things that we are doing here. So we know what is called orbit. Orbit is nothing but the sequence of the iterate of these initial conditions. Now we want to see whether these iterates are going towards somewhere or it's going towards infinity. That is our main question. So let me systematically, it's called the study of dynamics. So dynamics. So we want to study whether as time increases, or if I multiply with multiple times iterate, or if I see the population through time, whether the population will die out, that means what is the ultimate fate, or whether they will stay where we started. Suppose we started from x0, they will remain close to x0, so it will remain close to x0. So that is the question of stability, will come later. And third is whether this is periodic orbit or not, and fourth is obviously this is chaotic or not, or eventual periodic or not. So these kind of questions we are interested in, and to answer this question mathematically, we need to know whether what is the long term behavior of the orbit, means as time goes on how does this sequence progresses. So to see that, there is a concept is called the limit of a sequence. It's called the limit of a sequence. The limit of a sequence. Don't worry, this is a little bit mathematics, but it is needed, with this language is needed when we want to study under the mathematics these things, that any systems when we want to apply mathematics, we have to know this concept. So the limit of a sequence means, it basically means that whether these points will go towards a fixed point here. Suppose that limit will be that x0, these things, that the orbit is 0.5, then 0.25, then 0.025 so whether these will, we are actually, from seeing this pattern, we are quite sure that it will hit 0 at some point. So this 0 is actually the limit of that sequence. Now let us define mathematically. So limit of the sequence means, suppose we have a sequence x0, x1, xn, or suppose it's long. Now we will say that this sequence has a limit which is L if there exists a, suppose, n, and for all I which is greater than or equal to n, there exists a n for all I greater than n, and for every positive number, every possible positive number epsilon, you will find that xi minus this limit L, the distance between this xi and L will be always less than epsilon, so less than equal to epsilon. So if it holds, then we will call that the limit xn tends to infinity. So limit n tends to infinity, xn will go to L. So these basically, let me give the example so it will be clear. It says basically nothing. So it says that, suppose let us get back to our example. So here the sequence is 0.5, then 0.25, then 0.0525. Okay. Now when we will say that this has a limit 0, so I will say, suppose that I choose, first of all I choose, suppose epsilon equal to, suppose 0.25, and you know that if I take n equal to 1, so I know that for n greater than 1, all iterates value will be less than equal to epsilon. So x1 minus 0 will be less than 0.25 because x1 is 0.25. So this satisfied first. Then I will see the x2 minus 0, whether it less than 0.25 or not. So x2 means 0.025. So 0.0525 minus 0. So it is actually less than 0. If I go higher iterates, you see, if I go higher iterates, you will find that this relation satisfied. Now if I say no, I don't want to choose epsilon equal to 0.25, I choose smaller than that, I choose 0.0001. Now then you have to iterate this. Suppose n equal to 10, and you see that after n equal to 10, this iterate becomes 0.00005. Suppose that after iterate n equal to 5, it becomes like that, n equal to 0.005, and you find that n equal to 10, and you can say that yes, there exists n equal to 10, after which every that n equal to 11, n equal to 12, n equal to 13, it will be the distance between 0 and that will be always less than 0.001. That is basically says that this sequence has a limit which is 0. Is it clear, Subhaji? So that is a basically mathematical concept. Is it clear, Subhaji? Okay. Are you there, Subhaji, or you have left the meeting? Okay, that's the thing. That's the sequence. Now, don't worry about these things very much, because this is actually basically language. Other than that, it is nothing. And let's go further. Now, what we will see that we have see the sequence or these things. Now, okay, okay, it's fine, it's fine. If any question, you can write me here, so I can, and if it is clear, then it is fine. Then I can go to the next thing. Okay, then I'm going to the next thing. Let's. Okay, so next thing is, okay. Oh, that is it is fine. Then it is fine. Okay, let's go towards the next thing. So next thing is, since we now we know the language, and we'll say that this is argumentatively approaching or not. So now what we want to see that it's called the linear map. That is, we want to check the stability. So to check the stability, it is a very systematic approach. That is a very systematic approach which is called linear stability analysis. So this linear stability analysis analysis, this is the backbone of whole nonlinear dynamics. So whenever you are dealing with any nonlinear system, the linear stability analysis is the ultimate thing that you are going to use. Now in the case of linear stability analysis, you have to know the property of some linear map. So now let's going toward what is the behavior of the linear map using the cobweb diagram. So let's see that. So let's see, and uh, we will will see some theorem here, and after this class I will show you how this the linear this by using this linear maps property, we can say very we can say lots of things about the dynamical system. Let's see, first of all, linear map. Okay, linear map. Let's see, linear map. Okay, so linear map means that my map fx is basically some a into x. So that is the linear map. So it will be linearly dependent with x. So now one can say that what is the difference between this and the identical map? Identical map is nothing but y equal to x. So let me draw this. First let me see what is the fixed point of this linear map. This is, suppose this is y equal to x, suppose this is 1 and this is also 1, so this will be some 1 1. Suppose this is y equal to x. Now I have to draw, this is y equal to x. Now I have to draw fx equal to x. Now depending upon a, the line will be there. So first let me draw whether a greater than 1. So if a greater than 1, then it will be y equal to, so y equal to ax. Suppose this is y prime equal to ax, x0, and here this y will be x0. Since a greater than 1, we can see that y prime is greater than y. So suppose this is this is suppose x0, then this will be the y, this will be the y equal to x0. And for the case y prime, that this curve will be, y prime will be here somewhere higher, somewhere there, then the curve will look like y equal to x. Suppose this will go towards, suppose this point is not there, this curve will be look like this. And if a is less than 1, then obviously then y prime will be less than y, then the curve will be look like this. Now depending upon a is called the tangent of the curve, so depending upon the value of a, this the tangent of this black line will be different. Now what is the fixed point? So fixed points, here you can see that fixed point, the linear map has only one fixed point, which is x equal to 0. X equal to 0 will be the only fixed point. Now let us see by using cobweb diagram what is the behavior of this linear map. So what could be the possible cases? So let me, first possible case is, there are 4 possible cases. One is a is between 0 to 1. Second case is a is greater than 1. Third case is a is between 0 minus 1 to 0. And fourth case is a is less than minus 1. This fourth case is there. So we will see the behavior of the system one by one. Let me first see by using first one. So let's see. Okay, let me draw. Suppose this is 1, this is 1, so somewhere this point will be 1 1. Okay, now from here to, if I draw this is my y equal to x curve. Now I want to see this, that means a is less than 1, and we drawn that if a is less than 1, that curve will be below this curve in the positive coordinate. So this will look like that. Okay, this will be y equal to ax. Okay, now let us draw a cobweb diagram to see the fate of the system. Okay, let's draw cobweb diagram. Suppose our system start from here. So this is my initial condition x0. So what I will do, I have to do first draw vertical line up to here. Vertical line up to here. So the where the first point hits, that is y equal to ax0, that is x1. So this point is x0 comma x1, and this point is x0 comma x0. Now where it hits, from here we have to go horizontal right. So it will go like this. So here we will get a point that is basically x1 comma x1, and from x1, so this is my first iterate, that is x1. Now from x1 if I go here, I will get the point x2, so that is x1 comma x2, and again if I go from here horizontally, we get a point here x2 comma x2. Now here if I go vertical again, we get x2 x3. So this is x2, then here. So here we can see that these are approaching towards these fixed point x equal to 0. So from this cobweb diagram we can say that for a less than 1, means if a belongs to 0 to 1, the iterates will go towards x equal to 0. So ultimate fate is ultimate fate or the orbit is nothing but the sequence of the iterates of the initial point. So we can see that x0 x1 x2 x3 dot dot dot, it actually going this sequence. If I iterate it multiple infinite time, that means limit n tends to infinity xn, it will has a limit that is it's going towards 0. This is the first case. uh, so so Pusachi, how much you have means up to where you are there in the meeting?
Yes, yes. I was in the meeting till last. You just left.
Okay, okay,
It's okay.
okay. Then so it has a link.
It is very much network issue. Very bad network issue.
Oh.
Okay, it's no problem.
So it has a limit, so x equal to infinity. So I request you to means draw the cobweb diagram for a greater than 1. So if you means if you draw by yourself, you will get the feel that suppose that there is a function fx equal to ax, and where a is greater than 1. This will be kind of homework for you, means if you want to see the means cobweb diagram, then for what is the behavior for this behavior of the system when fx equal to ax and when a greater than 1. So that's it. Now I will show you for 4, option 4, that is suppose this okay, anyone. So 4, so you will do as a homework the case 2 and 3 where a is greater than 1 and a is between -1 to 0. So let's see linear map, fourth case. So we have seen the first case, we have seen if a is between 0 to 1, then the system always go towards the fixed point x equal to 0. That's a very important thing. We will see that it is always true, and this is the main thing of the linear stability analysis. We have to check what is the after the linearize the system, what is the if I have a non-linear system, then I have to linearize the system and I have to check what is the value of a. A is less than a is remain between 0 to 1 or it is greater than 1. So that is the main thing. So let me draw the cobweb diagram for a equal to -1. Okay, now here this is again this is my identical line, that is y equal to x. Now what is there, that is means a is less than minus 1, this y equal to x. Suppose let me draw also y equal to minus x. This will be y equal to minus x. Now I have to draw this line, that f of x equal to ax, where a is less than minus 1, right? Let me use that. So y equal to 1 is ax, so that will be minus less than minus 1. Suppose minus 1 means minus 2, so y will be minus 2x, and this is minus x, so this is y prime is minus 2x, and y will be minus x. So it will be always, y will be always, is minus x will be always greater than minus 2x minus y prime. So this will be here somewhere. Okay, y equal to, if a is less than 1, so the my curve will be here somewhere. So suppose it will be here somewhere. Okay, this is my y equal to ax, where a is less than minus 1. Let me now remove this line. Okay, now let us see. Let me draw it up to here. The behavior of this point, any point. So here also one fixed point is there. Now let me behavior of any point x0. So what we will do, from x0 we have to generate the x1. How we will generate? I will draw a vertical line until it hit this y equal to x. So that's how we get the x1. So this point will be x0 comma x1. Now I have to generate x1. To generate that, I have to draw a horizontal line here. So that's how we get this point, that will be x1. Now from here I have to generate a second iterate, that will be, so from here to here, here to here, here, so it will hit here. So it is basically x1 comma x2. Now we have to generate x2. So to generate x2 we have to do this. X from here to, we have to draw a horizontal line that will look here, that we get this point. This point is basically x2. Now from x to x2 we want to generate x3. For that we again draw a vertical line. Okay, it's going further. This is x2 x3. Now that's how you see that this x0 point, now it going out towards in this fashion. Now here if you see from here, it will again go here, and you can see that these points basically x0, from x0 to it goes to negative this side, then it came back to positive. This is x0, this is, suppose this is x0, this is x1, this is x2, then this is become x3. So basically this initial condition first go to negative, but the value of the negative is higher than this x0, and then from x1 it goes to x2, that is also higher than x0, then x2 to x3, then x3 is also, the the magnitude of x3 is also higher than the x0. So you can see that it move further away from this fixed point, move further away from this fixed point. So it's kind of diverging series. It is not coming toward x equal to 0, but it goes towards the x equal to plus minus infinity. That's how you can see that this fixed point is unstable, or you can see this fixed point it basically says this fixed point is unstable, or you can see this is backward asymptotic to 0, but that's very not the actual language we will use. So for all case where a is less than -1, the behavior of the system will remain same, and you can see from the cobweb diagram, and we will prove these things in the next class, that for a is less than 1, you see that your fate of the system is that will be diverge, that the fate of the system is that going toward plus infinity or minus infinity. That is for the a equal to -1. Now your homework will be, because if you draw a cobweb diagram by your in your bare hand, then you will feel that how it is actually generated. And the thing is that these things are very important if you want to know the nonlinear dynamics, because to see a system fate through a mathematics or mathematical model, you have to know that how to simply generate the cobweb diagram. So that's it. So your homework will be, so these two cases, for 2 what will be the behavior for a greater than 1, and 3 what will be the behavior between 0 to, okay, if a remains between -1. See, these two cases will be interesting. So that's it. That's it, Subodhaji. So let me end this class here, and the next class we will see is called the we'll see that there is another thing, affine map. So we'll see that the affine map, and then we will see the linear stability analysis. So that's it. So if you have any question, then you can ask me, or we can end this meeting here.
No, I have no specific question, and I will try out the cases. And but I want to say something, that is with the word chaos, it comes something known as the butterfly effect. So if you just discuss it, this phenomenon in the next class, it will be very much helpful.
Butterfly effect. You want to know the butterfly effect?
Yes.
Okay. I can tell you, but to know the butterfly effect mathematically, you know so many things. So okay, I will try. I mean, in colloquial language, means not using so much mathematics. If I can say the butterfly effect. So butterfly effect means basically the sensitive dependence of initial condition, that basically manifests the butterfly effect. And there is a concept of fractals. Okay, let see, can I introduce the butterfly effect in
Okay, if it is not possible in the next class, you can also in the next few, after you can say this in the next few after next few classes.
That is possible.
Because
I will
yes,
touch upon those things, means where means
yes,
I am
yes.
just because since I want to make this class in such a way that if anyone does not know anything about the linear stability analysis or the tools of nonlinear dynamics, then he can grasp the concept of chaos. So to go towards the concept of chaos mathematically, at least, means in colloquial language we can means discuss those things, but to see those things, the beautiful chaos in the mathematical term, you need some things like the linear stability analysis, what does mean by the periodic orbit, what does mean the dense periodic orbit, what does mean by the sensitive dependence of the initial condition, and then you can go towards the thing, that butterfly effect, that is the Lorentzian. If you solve the equation, Lorentz equation, that equation will be look like the if you solve that equation, that orbit of that things, as we are study the orbit, so the orbit of that things will look like a flapping butterfly wing. So from that term it is called the butterfly effect, and basically butterfly effect means the sensitive dependence of the initial condition. And to know the sensitive dependence of the initial condition, you have to know these things a little bit. So that's it. Now we will touch upon those things. So thank you for joining.
Okay, thank you. Thank you.